Is that where we need to like state the percentage error or something like
No. Hypothesis test, it's like null hypothesis, alternate hypothesis. We'll see. Let's see. So you can test hypotheses looking by just taking a sample. Aha, so this is a sample. This time it is the standard deviation out of the sample size. Okay. Let us see. Okay, let's try this one. So it's normally distributed. It's usually 3 squared. This thing. Would be the variance. The company claims that the mean amount of juice is 60. Okay, mean of 60. A trading inspector received that they're overstating the mean. Random sample of 16 finds it's 59.1. Okay, wait, how do we do this one? Let's see, normally distributed. And so normal distribution. Yes. So basically, we assume that they're telling the truth. We assume that the mean is 60, standard deviation is 3, and then we find the probability of getting like 59.1 or less.
Okay.
Let's see. So do you remember how to do that?
So if I go to statistics.
Yeah. Statistics, distribution. Normal.
Yeah.
Normal cumulative. So deviation 3. Mean 60. Let's see. What is lower? What is upper?
Will it be like lowest 0, upper 60 or something like
That would give you exactly 50%. The mean.
that? So we're doing 5%.
So you would do the upper is 59.1 to check their claims. And
Okay.
the lower, I'm doing minus 999.
Yeah.
If memory serves, that seems wrong. That seems very wrong. Okay. Let me see. Standard deviation. Oh, of course. That's why. Sorry, go back. They took a sample of 16 cartons. And so the standard deviation is 3 out of 16. 3 divided by 16.
Okay.
So mean is 60, standard deviation. Where am I going wrong here? Oh. I did 15. It should have been 16. Let me see their one. not converting something? What am I not changing here? Okay. So it was 63 squared. X is normally distributed. So sample size was 16. So it's the 0.75. That's 3/4. Why is 3/4? 0.75. Where does 0.75 come from? Did I forget to do something? Uh, 3/16. So 0.1875. Okay, hang on. So big picture is null hypothesis is they're telling the truth. So the null hypothesis is this one here, that the average is 60 milliliters of juice per carton and the standard deviation is 3 milliliters. The null hypothesis is that the mean, so the null hypothesis is that the mean is 60. The alternate hypothesis is that the mean is less than 60. And so to test it out, we assume, so X bar is normally distributed. It has a mean of 60. Well, hang on. We have, we're taking a random sample of 16 cartons. And so the standard deviation will be 3 out of 16. Variance 3 squared out of 16. We definitely know that the standard deviation has changed. We don't know if the mean is less or not. So we just keep the same mean. And then we check what is the probability that this new X is less than 59.1. Let me see. No. That's why. Sorry. We have to check that the mean. What is the probability that the mean is 59 or less? Yeah, less than 59.1. Do we have to do z equals x minus mu over d to get the new value? Is that what we had to do? Let's see. 60 over 3 squared. X is normally distributed 60, yeah. Oh, it's just the square root, sorry, that's all it is. 3 squared over 16. That's it, sorry. Got there in the end. The standard deviation is the square root of the variance. And so the standard deviation is the square root of 3 squared. So square root bracket 3 squared over 16. And it's 0.75. That's it. And so that's what goes into the calculator. You get 11.5%. Let's see. And so there's an 11.5% chance, basically 11.5% of the time that you take 16 random cartons, you'll get a mean of 59.1 or less. You need a 5% level of significance, and so it's not significant enough. it would have to happen only 5% of the time or less. It happens 11.5% of the time. And so the company is telling the truth. It's just random chance that it was a bit less than 60 in this case.
Okay.
Sorry about that. I forgot the square root, unfortunately. Okay, we'll try another. Let me just make a note to myself. Yeah, that's going to be square root. Okay. Let's see. So this is exam question. Let's give it a go.
Okay, so should we go to our normal distribution, our calculator again?
Yeah, hang on. Let's just set it out first. So the masses of penguins, so it's normally distributed. So X is normally distributed. Okay, what's mean? What's standard deviation?
Mean 5.9, standard deviation 0.84.
So the variance, we usually how we write it, 0.84 squared. Okay, random sample of 16. And so that is, let me just, yes, so X is normally distributed. Sample X. For our sample of X, what are the values?
So is it now going to be 6.6 and 0.84?
Well, we assume that the mean is the same because we're not certain. Variance?
One.
Variance will be, well, it was 0.84 squared. It's now 0.84 squared over 16.
And so I got 0.0441.
So what was the mean in the calculator?
The mean is 5.9.
And how do you do standard deviation?
Sorry, system distribution normal standard deviation. And in this case, are we putting it as 0.84?
Because we have a sample, we have to do, well, usually it's just the square root of 0.84 squared, which is 0.84. We have to do the square root of 0.84 squared over 16. And so it'll basically be 0.84 over the square root of 16, or just the square root of the whole thing. So I got 0.21. It's basically 0.84 over 4, the square root of 16.
Okay.
Okay, what is lower, what is upper?
Lower minus 999. Upper is it now going to be 5.9?
Mean is 5.9.
6.6, sorry.
So I believe it's going to be other way around. I believe lower will be 6.6, upper 999. Let me see. What is he claiming? Yeah, he believes that these penguins have larger masses. So average mass is 5.9 kilos. Standard deviation of the sample of 16 is 0.21. He wants, what's the probability of getting a mass of 6.6 or bigger? So you do 6.6 lower, 999 upper. And so what's the probability for that one?
So that will be I got 4.2906 times 10 to the minus 4.
Yeah. Excuse me.
Bless you.
Cheers. Let's see. So that is, that is 4 zeros. 1, 2, 3, 4. 429. Don't forget the decimal. If we times that by 100, it is 0.0429%. Let's see. So if you have an average of 5.9, standard deviation of 0.84, and you take a sample of 16, the odds of a random one being 6.6 or more, that happens like 0.04% of the time. And so what does that tell you? Does that support his hypothesis or not that Gentoo penguins in captivity have larger masses?
It probably supports it.
Yeah, definitely supports it. So, this previous one, 11. So they were saying like, what's the odds that if you take 16, the average will be 59.1? The odds of that happening are 11.5% of the time, and so 11.5. So it's a bit less than the mean, but it happens about 10% of the time just by chance if you take 16 randomly. And so it's not rare enough to meet the 5% level of significance. This time, this almost never happens by chance. Like the probability of it happening where you take 16 penguins and the mass is 6.6 or more is like less than 0.5%, much less. And so it's very significant. And so it's not just random chance, they are actually, it does support his hypothesis. So supports hypothesis, or there's a specific way. There is evidence at the 1% level of significance to suggest, etc., etc. Here we go. Here's all the stuff. There, we reject the null hypothesis. There's evidence for the zoologist's claim. Yeah, so the null hypothesis was that the mean is 5.9. The alternate hypothesis is that the mean is greater than 5.9. Grant. They did it a slightly different way. I'm happy. Let's see. All right, let's give this a go.
Okay, so we see that. So we know that standard deviation squared would be 3.11 squared.
Yeah.
And 25 recorded daily means. Oh, is the mean going to be 12.2?
Mm-hmm.
And do we now need to do a separate one where it's where it's still going to be 12.2 again? But this time, are we doing something like 3.1 squared over 9.5?
Over n, the number in the sample.
Is that 25?
Yeah, and it's very common. It's very common that they'll use a square number like 25, 16. Okay.
And do I now? So I need to do like x should be greater than 9.5 knots.
Yes. So the probability that the sample x is greater than 9.5. How do we get that?
So do I need to do lower 9.5, upper 999? And then after that, am I doing 3.1 squared over 25?
Square root of that.
Okay. And then do I do 12.2?
Hold on.
And I got 0.9999334.
That seems wrong somehow. Let's see. Standard deviation of 3.1, random sample 25. Given that the mean of the sample is 12.2, so they took a sample 12. Are they sneaking us? Hang on. Given that the mean of the sample is 12.2, test at the 2.5 level of significance whether the mean of the daily wins. What is this? The mean is greater than 9.5. They just phrased it a very strange way. Is the mean supposed to be 9.5? And the mean of the sample is... And that one's 12.2? I think it might be. 1 second. 12.2, 9.5. 12.2, 9.5. Yeah, other way around. They just phrased it a very strange way. So it's given that the sample mean is 12.2. So this was the sample one. And the actual mean is 9.5. So it's the other way around. So this whole question was phrased quite strangely. 9.5, 9.5, and we want what's the probability of 12.2 or greater. So what was that probability? So if you swap the two means around,
6582 times 10 to the minus 6.
Okay, so 6 zeros, 66582. Remember, decimal times by 100 gets rid of 2 zeros. 1, 2, 3, 4. Okay. And so our hypotheses. Null hypothesis, the mean is 9.5. Alternate hypothesis, mean is greater than 9.5. The probability of getting 12.2 is this amount. What does that tell you?
It's a pretty low chance.
So it's pretty low chance that it happened by random chance. Therefore,
Does that mean that the mean of the daily mean run speed is not greater than 9.5 knots?
it means it's definitely the alternate hypothesis. The chance of getting, if the average is 9.5 with a standard deviation of 3.1, the chances of getting 12.2, a mean of 12.2 are like very, very, very small, just by chance.
Yeah.
And so that's shows the alternate hypothesis. So this amount is less than 2.5%, and therefore it's the alternate hypothesis. There is sufficient evidence at the 2.5% level of significance that the mean is greater than 9.5. I hope. Sufficient evidence to reject H null at the 2.5% level of significance. So they use some strange numbers. Yeah, there is sufficient evidence to reject it. All right. Let me see. That's reading score, 7-year-olds. Yeah, all right. Let's try it.
So the first thing we're doing is putting mean 50 stand and then like 8 squared after.
Yeah. So x is normally distributed. Mean is 50. Variance is 8 squared.
And then after this, are we doing second one would be like 50, sorry. And then would it be 8 squared over 12?
Yeah. So sample x is normally distributed. We assume it has a mean of 50 and its variance is 8 squared over 12.
And so now, do we need to say that x needs to be greater than 50?
That'll be 50% exactly. Probability that x is bigger than the mean. So we want the probability that the sample x is greater than what?
Is it 54?
Yeah.
And so do we now go to the calculator?
Yep.
So are we then going to do like lower 50?
No.
I don't know. Is it lower 54?
Yeah.
Upper 999, and then do we do 50 and then square root of 8 squared over 12?
Yeah. So 8 over root 12.
And I got 0.0416
Okay. So what do we do with that?
Do we say that that probability of x is greater than 54 is equals to that?
Yeah.
And do we then change that number into a percentage after?
Yeah.
So if we do, we now need to do, which that would be about 4.16%.
Yeah.
And now we need to say we have to test whether reading for 20 minutes a day has improved reading scores.
Mm-hmm.
Do we have to say no because the number's below 5%?
Yep. Is that the answer? One more thing you need to say. And so, did it work? Did the reading scores improve?
I mean, the mean score suggests that they did.
So it went from 50 to 54.
Yeah.
But it might just be, we took 12 kids randomly, and these 12 have a mean of 54. And so maybe they went up, or maybe it was just random chance.
Yeah.
We checked, and the odds of it happening by random chance are roughly 4%.
Yeah.
And so, which is less than the 5% level of significance. And so, did their scores improve?
No.
Yes. So the null hypothesis, the one you assume, is that their average is 50. The alternate hypothesis is that the average went up. It's now greater than 50. The odds of taking 12 kids randomly and getting a mean of 54 is 4%. That's less than 5%, and so it's pretty rare that it was just random chance. And so therefore you're going with there is sufficient evidence at the 5% level of significance that their scores improved. Now it might just be random chance, but that only happens 4% of the time. Of all the kids, if you take it like 12 kids randomly with all these variables, the odds of getting a mean of 54 or more are 4%. And so because it's pretty rare, we say, yeah, their scores have gone up. That they really do have. Yeah. And so this is what it looks like. So you've got all the kids in here. what you would expect is you'd get some of the kids, in here with a mean close to 50. And so a mean of 54 out of that standard deviation is like very low chance, less than 5% chance. And so we say, yeah. Okay. Any questions about that?
No.
So it takes practice. It's not easy. Let's see. So a critical region. That's like, in this case, not really. I think I just want to see what they did. I think they've been finding the critical region. F and G. So they've been finding the critical region. That's how they do these questions. In this case, the critical region was 53.6. And so if you got, if you took a sample of 12 and got a mean bigger than 53.6, then it does meet the 5% level of significance. They got a mean of 54. And so, yeah, it's gone up. So one way is the way we've been doing it. Like, what are the odds that it was just random chance? Another way is to find the critical region and do it that way. So anything more than 53.63 would be the critical region. Let us see. We'll give this a go. So we have to find the critical region for this one. Let us see. So it's normally distributed. The mean is 0.580. The variance is 0.015 squared. A random sample, so n is 50. The distribution. Hang on. The machine is serviced, and after the service, a random sample of 50 is taken. Has changed. The distribution. Okay. I don't like this. 1 second. Yeah, they did two things at once. I don't like that. Let me see this one. I'll go back to that one in a minute. Explain the difference. Oh, okay. So they're doing two things at once. Looks like they're all going to be the same. 1 second. Yep. This looks better. Let's see. Deviation. They're all similar. Find can be sold 12 bolts are chosen. Okay, find the probability. No, it's strange that they're. Sorry about this. I just don't want to introduce two new ideas at the same time. Find the mean. Probability. All right, looks like I have to do it. Let's see. So, any idea for this one? What is the null hypothesis? Nah, it's not. Yeah. All right. So these. All right. You know the way before we were saying either it's this or more. Like, what's the odds that their reading went up? You could also say what's the odds that their scores went down. So you could get like left tail test, right tail test. If they ask what's the probability that the scores changed, that could be up or down. And so that would be half the level of significance. And so half at the top half, half at the bottom half. So that's how that works. So this one has a 1% level of significance, but we're actually going to do 0.5% because we have to look at the top half and the bottom half to see if it changed. Did it go up or did it go down? And so we have to half that. Everything else should be similar. Okay. The machine is serviced. Random sample of 50. Okay. So X sample is normally distributed. We assume same mean. This is going to be 0.015 squared over 50. The distribution. Yes, how do we do this one? We want to say what. So the probability that the sample X is greater than some number gives us 0.5%. 0.05. We have to find what number does that. Any idea how we go with this one?
Is it straight to the calculator?
It is straight to the calculator.
Okay.
So let's see. Okay, so let's say upper is 999. Mean 0.580. Standard deviation is 0.015 over root 50. Or just the square of the whole thing. Here's the long way of doing this one. We want a lower that will give us an answer of 0.05. So if the mean is 0.58, let's say 0.4. Hang on, 0.6. Oops. Okay, 0.6, no. 0.55. No, 0.59. Okay, so you get this small number. That'll take a very long time. Instead, you do distribution normal inverse. Yeah. And so it's inverse normal. And that's what you use to find what X will give you an area of 0.05. And you put in the rest of the values as normal. And so try that one. Did you get an answer for that one?
So I got 0. Sorry, I need to go back to inverse normal, my bad, sorry.
Yeah, inverse normal.
Yeah.
So basically area is probability. So this time we have the probability and we want what X gives you that probability.
I got 0.583
Okay.
Yeah.
And so yeah, that's a bit above the mean. And so now we want the lower part. So what X or less would give us also 0.05 on the other side of the normal distribution.
And so are we now making tail left?
Yep.
Is that all we need to do?
I think you're right. Yeah, I think you're right. So what is that one?
Yeah, 0.5765.
Okay. And let me just copy that. Let's see. It is... Yes. Yes, that's it. And so if you were to do what we were doing before, and you had this mean, this standard deviation, and you put in 0.57 or less, so like minus 999 as lower and that as upper, you would get roughly 0.5%. If you did zero lower as 0.585 and upper as 999, you would get roughly 0.5%. Yeah. Okay. And what is part B? So the mean diameter of the sample is this. Comment on this observation in light of the critical region. Any idea about that one?
I'm a bit confused, I think.
So remember we got this, one of our answers was 0.583.
Yeah.
So basically, if you get a diameter of 0.583 or more, then it's the alternate hypothesis that the diameter has changed in the machine. It has gone up. They take a sample, and the mean is 0.587, and so has the average changed, or was it just random chance?
Is it just a random chance?
If it was closer to 0.580 than 0.583, then it would be random chance. But it's further away. It's in the critical region, and so it's not random chance. It has it has changed.
Okay.
It's like the reading score, like, because it's rare enough. Let's see. That's part A. B. The observed value falls inside the critical region, and so the mean diameter has changed. Yeah. Okay, let's give this one a go. Let's just go straight to part B. This one here.
Okay. So do we go to our calculator again?
Yep.
And so is it going to be normal distribution?
Yep.
And so I'm just confused about the mean thing.
That's the same as, so the mean, that's the assumption that it's 34. For this sample size of 25, so sample X is normally distributed, we assume same mean, and it's out of 25. And so you have to say what values will give you a 1% level of significance. Any idea about that? So for other ones, it's usually say like greater than or less than, like maybe the mean went up or the mean went down. In this, it's not equal to, and so we have to split it into bottom half and top half. And so 0.5% for the bottom half, 0.5% for the top half. So basically, it's normally distributed. Mean is 34. Standard deviation for the sample will be the square root of 1.1 squared over 25. And we want what values here and here will give you an area in here of 0.5% and 0.5%.
Okay, so is this what we're doing, like left and right and stuff?
Yeah.
So inverse normal.
Correct. Inverse normal is to find the x that gives you that percentage. In the beginning, we were finding the percentage. We were given an x like 59.1 and we'd say it's like 4%. Now we're given the percent, we have to get the x that gives us that percent.
So for area, when I'm doing left and right and stuff, when I put area in, is it going to be 0.005%? No, 0.005.
Yeah, that is 0.005. Yeah. For 0.5%.
And then will this next one be 1.1?
This next one, so that's the deviation. The deviation for the mean?
Oh, is
for the sample?
Is it square root of 1.1 squared over 5?
Over 25.
Over 25, sorry, yeah.
I already square rooted both of them. It's just 1.1 over 5.
Okay.
And mean?
$34.
Yep.
Should I say what I got for left?
Yep.
I got 33.4.
do wrong here?
3.0.
1.1 over 5, so 34. I forgot to put in 34, that's why. 33 point something?
Yeah.
So 33.4, yeah, okay. And what about the other one?
And so now it's right, and it'll be 34.6.
34.6, that looks good. 34.6, let's take a look. Yeah, so sample X is less than 33.4 or sample X is greater than 34.6. Okay, and then part C, the sample is found to have a mean of 33.7. And so comment on that observation.
So if it's found to have a mean of 33.7, that's greater than the 34.
Right.
Oh, that's less than the 34, sorry. So does that mean that there was 0.3 off or something? Yeah.
So 33.7 is like probably about here.
Yep.
Okay, and so
did they what the bottom 0.25% of it?
0.25, sorry, what?
So is it because 33.7 is in between 33.4 and 34? Did they get like the bottom 0.25% or?
Where are you getting 0.25% from?
Because it's half of 0.5.
We already halved 1% to get 0.5.
Okay.
So basically this value of 33.7, is it very rare that it wasn't just by random chance, that it is significant, or is it common enough that it's just random chance?
Sorry, could you say that again, please?
So this value of 33.7, is that very rare that it is significant, or is it just by random chance that you would expect to get something like that?
Probably by random chance.
Correct. Yeah. So you can see how all this stuff in here, it's close to 34. And so that's kind of where you would expect. If this was like flipping a coin, that would be, like 100 times, or let's say you flip a coin 25 times. You would expect it, most of them, the number of heads and tails, let's say, well, I don't know. You'd expect most of the stuff to be in here. It's only the very rare stuff that's out here. Yeah, I'll say this is the height of boys. Most people, this is the average, bit shorter, bit taller. But if someone is like very short or very tall, that's kind of the significant bit. And so in this case, what's the odds of this happening randomly? It's just random chance. It's not outside of the it's not inside the critical region. This is the critical region in here, and we have another critical region in here. And so this was to check. It wasn't. It was just pure numbers. 33.7 is not in the critical region. Yeah, so this would just be the null hypothesis. You just go with whatever you assume. And so they're all going to be like that. So this one, you'll have like 5% here, 5% here. You have to, what is in the middle? What's the mean? Mean is 200. You have 200 in the middle. You would get the sample standard deviation, and you would say what X would give a 5% level here, what X would give a 5% level here, and then you would just check, is this bit inside the critical region where it's actually significant, or is it somewhere like in here where it's just random chance, a bit more. You flip a coin, a few hundreds of times. How many times does it land on heads? Let's say 400 times. It'll be a bit more than 200, it'll be a bit less. It might not be exactly 200, just random chance. Yes, and so that stuff, what do you give yourself?
I think overall maybe a tick.
Okay, so let me just see. Yes, okay, that's normal distribution finished anyway. Yeah, how was that for you, Andrey?
I think tricky initially, but I think I sort of get it now. Yeah.
So this takes practice.
Yeah.
And so mechanics next time.
Yes, please. Yeah.
Any questions for me in general?
I don't think so.
All right, well done, Andrey. You did great. I look forward to you talking again next time.
See you on Monday.
All right, have a good weekend. Take care.
See you. Goodbye.
Bye.